Hello everyone, this is the editorial video for static range minimum queries from CSES problem set. We are given an array of n integers. We need to output the minimum value in the range a comma b. So let's take this for an example. We need to output the minimum value in the range 2 comma 4, and 2 comma 4 is this range, and the minimum in this range is 2, right? So there are many ways to solve this problem. The very naive way would be to traverse from A to B and figure out what the minimum is and outputting it. But that would take up to n cross cube time complexity. We need a way to optimize this. And we can use some powerful data structures such as segment trees, but segment trees are quite hard to code, and segment trees provide a time complexity of log of n for every query, but we're going to use something which would give us the answer in O of 1 time complexity. So we're going to be using sparse tables, but I just want to remind you that sparse table cannot always give you the time complexity of O of 1. uh, it it can only give you the time complexity of O of 1 if the operation performed follows idempotency. Now, let me explain to you what idempotency is. So idempotency for any operation phi, for any operation O, A operation A should be equals to A. If anything follows this inequality, any operation follows this inequality, then that operation is considered to be idempotent, right? So 2 plus 2 is equals to 4, which is not equals to 2. So this does not follow idempotency. And minimum of 2 comma 2 is 2. So min operation does follow idempotency. And we are given the in the question of minimum queries, right? So this does follow idempotency. Now let's see how we can code this out. So I'll be using one right shift p in place of 2 to the power p, right? Now let's see. Now in a sparse table, we keep track of sum of every uh, block of size 2, and every block of size 4, and every block of size 8, and so on. So we keep track of the sum of the minimum of these two elements, 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 and so on. Similarly, we keep track of minimum of these four elements, minimum of these four elements, these four elements, and these four elements. Similarly, we keep track of minimum of these 8 elements, and if there were more elements here, we'll keep track of every power of 2, right? Now let's see how we're going to fill the array. Before I tell you how we're going to fill the array, now let's just assume we already have a segment tree created, right? We already have a sparse table built, right? Now if a query comes and it wants the answer from 2 to 7, right? From index 2 to 7. So what we can do is we can combine the answer of minimum of these four elements and minimum of these four elements, right? So if we combine the answer of a minimum of these four elements and minimum of these four elements, we will essentially get the minimum of this whole range, right? And as I told you, sparse table always keeps track of minimum of every 4 block element, right? So this is a 4 block element, so 4 block subarray, and this is also a 4 block subarray. We can easily get the answer for this, right? Now let's see how we're going to fill the array. So 2 to the power 0 is equals to 1. So keeping uh, at the zeroth index, we are only going to save these elements, right? Now for block of 2, we're going to save answer for these two here. So answer is 2. Answer for these two here. Answer for these two here, and so on, right? Now for every 4 block element, we're going to save the answer starting from here, the mm, minimum of block starting from here, right? So it's 2, minimum of block from starting from here and here and here and here, right? And then we'll store the answer of block starting from 3 of 8 size 8, right? So this is essentially what our sparse table will look like. We don't need to put values here, right? Because these all values are not accessible. They all go out of range. Okay, so this is how we build a sparse table. But uh, how do we build a sparse table efficiently? For filling up the ith spot, let's just say if we want to fill up this spot, right? This is of size 4. It stores the sum of size 4 block from starting from index I, right? Starting from this index. Okay, so what we can do is we can combine the answer of 2 size subarray with this 2 size subarray and figure out the answer for this 4 size subarray, right? So answer for this 2 size subarray is stored here, and the answer for this two size subarray starting from here is this, and we combine the answer for these two, which gives us the answer 1, right? So this is how we will optimally fill our array. Now let's move towards the code. First I've taken the input, and then I've created a vector of size 20 and then run the command build. Now in the build command, the first row is essentially this array, right? So we have filled the first row with this array. Now we will walk in the blocks of 2. We're going in blocks of 2. For size 2 block, we'll keep track of a head variable, which will essentially give us the maximum power of 2 less than 1p, and the maximum power of 2 which is less than 1p is 2 to the power p minus 1, right? So we keep a variable where we store the max power of 2 to the power p minus 1, right? Now we run a for loop from I to n, and for every element, for every p comma I, we store the minimum of p minus 1 I and p minus 1 plus ahead I. So what do I mean by ahead? Ahead is essentially when we want to combine the answer for these and these. So p of I, p minus 1 of I is this, and p minus 1 plus ahead is this. So we combine the answer for these two, right? That's all easy. And now we're going to query. So just for you know, compensating for indexing, we take L minus 1 and R minus 1. Now P stores the maximum power of 2 less than R minus L. Okay, so number of elements between R and L So our first example where we needed the sum of these six elements, we take largest power of 2, which is less than 6, and that is 4. Now we combine the answer from this, starting from this, and we combine the answer from, starting from this, and we get the total answer, right? Let me show it to you clearly. Okay, let's see here. Let's say we want the answer for these six elements, right? So we can get the answer for 4 block element starting from 2, and we can get the answer for r minus 4 block element, which is this. R is equals to 7 and r minus 4 is this. So this will store the sum of next 4 elements. Yeah, that's what we are doing. We get the answer for p comma l and p comma r minus power of 2 plus 1. So yeah, that's how we solve the problem. I hope you were able to understand the problem.